So first, let us review what we had in the last lecture. So actually, we introduced structure. So if I have G Lie group, and I have H inside G, which is Lie subgroup, then we defined structure of smooth manifold on G quotient by H. So this is smooth manifold. Such that the projection map from G to G of H, that is, I take an element G here and map it to the class with representative G here, is fiber bundle. With fiber H. And in particular, from that we concluded that a natural action of G on the quotient is smooth, and if H is normal subgroup, then the corresponding quotient is Lie group. So let us continue using that. So first, let us introduce new notion, so definition. So X inside Y. So this is smooth manifold. Y is smooth manifold. We should. So this is actually subset of Y, and so this subset is called immersed. Is called an immersed submanifold if, first of all, X is itself smooth manifold, but what's important, not necessary in the topology which comes from Y. So maybe with some different topology, not in the subset topology. And second, inclusion map of X into Y is injective immersion. So what does it mean? So if I have a map, so F is from one manifold to another, is called immersion. If kernel of the map of the linear map df at any point x is trivial for any point x in x. For example, this figure 8 example, it's an example of an immersed submanifold, but not embedded submanifold or submanifold in our sense, or irrational winding on torus, also an example of immersed submanifold. So what's important here is in embedded manifold, there's the additional requirement that inclusion map should not only be an immersion, but also should be homomorphism to the image. So, okay. Well, this being said, let us prove the following proposition. So, proposition. So suppose I have Lie group action of a Lie group G on some smooth manifold X. So Lie group action. Then orbit, any orbit, so G is orbit is what we have if we apply all the elements G to some fixed point, right? Is an immersed submanifold of G, of course. Sorry, not of G, but of X, right? So this is subset of X. This is an immersed submanifold, diffeomorphic to the quotient G, quotient by the stabilizer. So this is the stabilizer. So reminder that stabilizer is all elements G in G, such that G dot X is X itself. So this is true for any X, for any chosen X in. So let me insert it here. For any X in X, this is an immersed submanifold of X, diffeomorphic to the quotient of G by this Lie subgroup. And we know that this is really Lie subgroup. We proved it in the first lecture. Well, there's nothing really to prove. Just need to look carefully at what is going on here. So you have this map alpha x. So let us fix some point. Then you have this map alpha x from G to X, such that it takes an element G and gives you an element G dot X for this fixed X. And then image of alpha X is exactly the orbit, right, of an element X with respect to this action. And we have the following commutative diagram. So G goes under alpha X to X. And we also have projection P to the quotient. And then we have this map, which we call beta X, from here to here, which works as follows. Beta X sends class with representative G to the point in X where X is moved by G. And it's clearly it is clear that this is well defined. Yep? So if we choose different representative, then it will be the same point because the quotient by the stabilizer of this point X. Okay, and what we need to see that so we have that right. So we need that G dot X is an immersed submanifold. So we need to check whether d alpha X at any point G has no kernel. So this is one thing that we need to check. And another thing that we need to check is that this map beta X is diffeomorphism. So first thing to notice is that actually beta X is smooth map, right? Because again, remember this triangle, then we have, so this is fiber bundle, this is smooth, if and only if this is smooth. So, so bit actually, so these are two questions, right, that we need to answer in a positive way. So first of all, beta X is smooth. Since P is fiber bundle, and we had this lemma, which so this fiber bundles, they satisfy conditions of this lemma, right? And then so therefore we can consider differential of X, and so we have that alpha X is first apply P, then beta X. Then I can take differential at point G of alpha X, and this is d beta X dp. We just need to compute now ranks of all these three differentials that we have. Well, of course, I need to put some points in here, but well, actually it doesn't really matter. G here, and then class of G here, right? And so I have that rank of alpha X. So this I know that rank of alpha X is codimension of Gx. This I know from just the theory of smooth manifolds and the theorem of map of constant rank, which is this alpha X. And Gx is the preimage of alpha X with respect to alpha X of the point X. And this is dimension G minus dimension Gx. On the other hand, what is rank of P? So this we also know. because, well, in coordinates, in some coordinates, p is just forgetting some number of the last coordinates, right? So p is actually map of full rank, right? So this is actually the dimension again of g over gx, and this is exactly, so forgetting first number of coordinates, right, means that, well, we have rank of this map is dimension of the manifold where my p goes, right? Well, maybe I should add d here, right? So this is dimension of this is dimension of g minus dimension of gx. So we have that rank d alpha x is the same as rank dp, and suppose then that d beta has kernel, then this would violate. So this would violate this statement, right? So from here we conclude that d beta x is so has no kernel. In particular, this is a map from between two manifolds, smooth map between two manifolds of the same dimension. It's locally invertible, so it's local diffeomorphism because of that. But this is also injective map, just from the construction of beta x. And so beta x is injective. Right, so therefore beta x is diffeo. On the other hand, we also need this, right? But we already see that rank of d alpha is codimension of g of x. So therefore, if I have had something in the kernel of alpha, right? Well, so this is an immersed. Well, sorry. Actually, this is it's not what we would like to see, right? So kernel, of course, we have some kernel here, just because this is this might be. So this is what we need is actually that this, right? So this is an immersed submanifold, and this is an inclusion map, right? And we need to check that the inclusion map is an immersion, right? So therefore it has no kernel. In particular, it follows from here, right? So actually what's needed is that beta x is diffeomorphism, and then it proves everything. Well, it's diffeo. Sorry, again, just to make sure that. So I need to put gx in here. G dot x. Then beta x is diffeo. Right. So now if everything is correct, right? So beta x is diffeo. Of course, to the whole x is not diffeo because the whole x might be bigger than one orbit, right? So Vtx is differ to just one orbit. Okay. So therefore we got this proposition that we'll use in a minute when proving homomorphism theorem. Okay. So next notion that we need. Next notion that we need is virtual Li subgroup. So definition. So suppose I have H inside G, and G is so H is called. So H is called virtual Li subgroup. If, yes, so first of all, we of course would like H to be just abstract subgroup, be closed under group operations. And second, we require H to be an immersed submanifold. Right. Well, H, and of course I would like H to be Li group in the beginning, right, with some structure, right? So H, so G is a Li group, and H is another Li group. So H and G here are Li groups. Okay, so this is definition, and now, so the standard example of virtual Li subgroup, which is not a Li, which is just not a usual Li subgroup, or in our sense, is the irrational winding on torus. So just to recall, so we have torus, which is S1 times S1, right? So I guess I should write ones here. So this is circle times circle, and I have W inside T, right, which is given by the following. It is e to the I t, e to the I alpha t, where t runs over R, right, and alpha is not in Q. So then the statement is that W then is virtual Li subgroup of T, but not a Li subgroup of T. Again, in different sources, people use different terminology. In particular, it might happen that what we call Li subgroup is called closed Li subgroup, and virtual, what we call virtual Li subgroup, people call it just Li subgroup. But okay, that's the terminology that we use. All right. So finally, we can formulate what's called homomorphism theorem. The kernel part of it we already discussed. Right. So okay, maybe even before homomorphism theorem, sorry, we can introduce yeah. So okay, homomorphism theorem. So theorem, which is called the homomorphism theorem, it says the following. So suppose phi from G1 to G2, it's a homomorphism of Lie groups. Homomorphism of Lie groups. Then, first of all, kernel of phi, which lives inside G1, is a normal Lie subgroup. And second, so kernel of phi. And second, image of phi, which lives inside G2, is a virtual, and this is important, virtual Lie subgroup isomorphic to G1 quotient by kernel of phi. And the proof is you just need to apply everything that we learned about actions to one specific action of G1 on G2. So proof. We know that G1 acts on G2 as follows. I take an element in here in G1, act on element in G2 as follows. First I apply G1 and then multiply by phi of G1 from the left, an element in G2. Then kernel of phi is exactly pre-image, well, it's exactly stabilizer in G1 of identity in G2. So therefore the first part follows, and that we discussed already last time. And well, image of phi right is exactly so image of phi is exactly so it's orbit of E with respect to this action. So with respect to action alpha. And we know that an orbit of Lie group action is so we just proved it in a previous proposition that it is an immersed submanifold, right? In this case of G2, and moreover it's isomorphic to the Lie group quotient by stabilizer, which is exactly the kernel, and therefore part 2 follows. So actually this is just application of previous proposition and of theorem about stabilizer of an action to one particular action, to this one. Okay. And well, this is an important theorem, which, well, this is usually what somebody wants to know when they define homomorphism, some map respecting some structures. So whether it has kernel and well, whether the kernel of this map is inside the category, so to say, that we defined, and whether image of this map is inside this category. And so the answer is yes for the first question and almost yes for the second question. Right? All right, so maybe a couple of examples of this situation of the homomorphism theorem. So actually there is a map F from R to S1. I just take an element in R and map it to E to the 2 pi IT. Then the kernel of F is exactly integers in here, right? And we then can write that S1 as Li group is isomorphic to real numbers quotient by normal subgroup inside, which is Z. So this is an illustration of homomorphism theorem, like one of the more elementary ones. Okay, and maybe another example, just to make more than one. Well, we can consider affine transformations and map it to all inversible linear transformations. Well, it's clear in what fashion, right? So affine transformation is a transformation of such kind: x goes to ax plus some vector b, and we can map it to well, ax here to A, right? And then as Li groups, GLN is isomorphic to affine quotient by Kn, right? So here B lives inside Kn. So Kn is an abelian Lie group, lives inside affine. And it is normal, moreover, we quotient by it and get, as a result, Lie group GLN. Another example. So finally, before going to Lie algebras, let me introduce the notion of homogeneous space. So definition. So a homogeneous space is a smooth manifold X together, so it comes with Lie group action. So, and actually, in what is important, it is transitive. So, transitive Lie group action. So, some Lie group acts on X. And transitive means that actually x is a single orbit of this action, right? Any 2 points are related by an action of an element in G, right? And then this proposition that we proved today, which says that an orbit is isomorphic to G over stabilizer, right? Says that then if X is homogeneous, X is homogeneous space, then X is diffeomorphic to G over H for some normal subgroup H. Normal Li subgroup, which is the stabilizer of some point. And sometimes people just call homogeneous. So what is the conclusion? Is that homogeneous space is the same as quotients of Lie group by a normal. In this case, this subgroup not necessarily should be normal. By Lie subgroup, not necessarily normal, right? Because, well, X is not necessarily Lie group. It's just a smooth manifold. Okay, and so sometimes people just call homogeneous spaces such quotients. Sometimes they just call homogeneous spaces smooth manifolds with transitive actions. So these are the same things. Examples of homogeneous spaces. Well, there are a lot of examples. One very known example that I would like to present is a sphere, right? N sphere, and S or n plus 1, so all orthogonal, or maybe even I shouldn't take special orthogonal, well, I can consider orthogonal group which acts, of course, on Rn plus 1, right? But it leaves the n sphere inside Rn plus 1 invariant. So therefore it actually acts in here. And if you look at the stabilizer of some point, it will be exactly On. So therefore this is diffeomorphic to On plus 1 by On. And this action is transitive. All this is, of course, it's not obvious, but it's easy to check all these statements. But this is one example. All right. So let me. So this is the everything that I wanted to say about homogeneous spaces, and they are very related to homomorphism theorem. So now we can actually go to tangent spaces of a Lie group at identity, and these tangent spaces, because I have multiplication, these tangent spaces have additional structure, which is called Lie bracket. And with this structure, they become what is known as Lie algebras. So let us now go to study this additional structure. So again, let me consider some Lie group. And let me denote by G the tangent space of G at identity. And let me consider chart of G which goes from U to K n, where n is the dimension of G. So this is chart of G. Such that, it is chart around E, and I would like it to be centralized in the sense that phi of E is 0. I can find such a chart. All right. And let me introduce some notation that I would like to use. I would like to, so if I have an element x in U, then I denote by x bar an element in Kn, which is given by phi of x. It's just a notation. Let me actually consider smaller, for just, I will need actually not only U, but smaller open subset inside U. So such that if I consider group commutator, so group commutator I will actually denote like this, and this is by definition x, y, x inverse, y inverse. So group commutator of two elements inside V is inside U. The only reason is that I would like to consider coordinates of such thing and their dependence on the coordinates of x and y. So this inside U for every x and y in V. So, okay, so these are some technical preparations. So I would like to discover a Lie bracket in here. So this is my goal. And this is some operation that depends only on my group. And it's smooth and group structure. All right. So let me now take my group commutator. So let me fix some x and y in V, consider group commutator, and consider its coordinates. So these are just some number which are of course. So I would like to consider this as a function of x bar and y bar. Right, x and y, they have some coordinates, and this element has some coordinates. And so I would like to consider this as function of coordinates of x and y. And then I would like to expand this as Taylor series. So consider the Taylor series of this as a function of x bar and y bar. Well, it will have some constant, then linear terms, and then quadratic terms, and so on. So this is constant, this is linear, this is quadratic terms. Now I would like to make an observation that actually C and L are 0. And so maybe in form of proposition. So then these dots mean that I have terms of high degree in x bar and y bar. And proposition is that actually C is 0 and L is identically 0 for any x and y. And actually Q of xy has the following form. It is sum. It consists only of mixed terms. xi, yj, cij for some numbers cij. Well, these are not numbers, so of course, right. So my x bar, right, is just to be more specific, it's a tuple of variables, right? It's a coordinates of x. And y bar, they consist of y1 all the way to yn. These are coordinates of y. And so therefore q should be an element in kn. So there should be n numbers, right? So actually, like a kth element, like kth entry in this vector, right, is of this form. So what I said here is actually in general a quadratic term would also include something like sum aij xi xj and sum of b with some coefficients of yi yj. So what I am saying in this proposition for this Q is that this Q is such that these terms are not present in this Q. Only this mixed term. All right. So then what do I have? I actually, so how to prove this? The proof is easy. It's just actually uses the only one observation and its variations. So if I consider a group commutator of x and e, right? It is what? I should, instead of y, put identity in here, and I will get x times x inverse, which is just identity. So this is E. So this means that if instead of y in the right hand side, so y equals E, it means that yi's, they're all zeros, right? My chart is such that phi of E is 0, right? So this thing means that if I put instead of y 0 in here, then the result should be 0. In particular, it means right away that the constant term is 0, and all terms which depend only on y without x, they're also 0. Right? It means that we already avoid this, right? Not this yet, but this one, and linear terms in y we also avoid, right? But we also can use the same argument and write this. Because if you instead of for any y, if you put E in there and compute the result, we will just E. And it means that if for any y, if I put x inside, if I put instead of x 0 here, then the result should be 0. This means that linear terms including x are gone, and terms of this kind, they are not there. So we already see that from these two lines, C0L of xy is 0 and Q has such a form. So we proved the proposition. Now we are ready to define a break. Okay, so definition of Li bracket. is this. So Lie bracket is binary operation, actually bilinear map from G times G to G, which is defined as follows. I take two vectors, like a pair of vectors, one from here, another from here, say psi and eta, and then bracket of these things is defined as follows. So it is d. All right. So I can. Well, let me just write the formula to be clear. So I take differential of my chart. This is my chart. Differential at E. And I would like to actually take inverse. Right? So this will be a map from, so differential is from tangent space to tangent space. Inverse of a map is from Kn to U. Differential of Kn is Kn. And the differential of U, well, at identity is G. Right? So it is an element in Kn, which is Q of what? Of what? D E phi. So this is this. I should put parentheses here. D E phi of psi. D E phi of eta. Again, let us just make sure that everything here makes sense. So psi and eta are elements in G. Differential of phi takes an element in G and maps into the tangent space of Kn, which is Kn itself. So these are elements of Kn. And Q is a form on Kn, right? It is exactly this Q that I have here. So it eats two elements of Kn and gives me another element of Kn, which then by this map, I map to the element of G. So this whole thing is inside G as needed. And this is the definition. Well, the idea is very clear, right? So I actually take quadratic. So I have multiplication, right, in my group. Well, for some reason, just to make it not dependent on a chart, I should go from I should take rather than multiplication, but group commutator, and look at quadratic terms in this group commutator. It's actually the first non-trivial term in the Taylor expansion, and this defines me some structure on the tangent space. And this is the definition. Okay. So what we would like to see is that this does not depend, so this bracket that we have, as it is, it looks like it depends on the choice of the chart, but we would like to see that it actually does not depend on this choice. So proposition. So Lie bracket does not depend on phi. You can choose any other chart with such properties, and the result will be the same. if you fix xi and eta and define bracket with different chart, the resulting vector that you have here will be the same. Okay, let's prove this. Suppose I have two charts, phi1, right? It's one chart, phi2 another. And to distinguish, so we used here notation bar, which is coordinates in this chart phi that we fixed, right? So now let x bar be phi of x, phi1 of x, and x double bar be phi2 of x. Right? So this is for any x and y in u1 and u2 respectively. Okay. Then, all right. So what I would like to compute is the following. So let me take x and y group commutator and consider its coordinates in the second chart. Okay, so on one hand, it is what? So it is some matrix, right? So it's a vector. It is obtained from coordinates of x of this commutator in the first chart with some matrix, right? So actually, this matrix here is this thing. It's d phi 2 inverse d phi 1, and everything is in so these are all differentials at E, and right. So actually this have, so actually I have some other terms which are terms in xy bar of degree higher than greater or equal than 2. So actually what I have is that for any x double bar is c x bar plus terms of degree greater or equal than 2 in x bar. And what I have here is just, so this is for every x in u2 actually intersect u1. Right, so that these two things make sense. So I just take this and apply it to x to this element. So again, I'm just considering x and y close enough to identity, so they are in the corresponding open neighborhoods of identity, so that all these formulas make sense. Okay, so then I can take this, right, and now use this formula, right? And we know that C and L are zeros, so therefore this is C Q of X bar Y bar, right, plus terms of degree greater or equal than 3 in X bar and Y bar. Now I would like to go back I would like to go back to variables x double bar and y double bar, and I'm using this. Well, not this, but the opposite of this, where I need matrix C inverse. Let me see. I think the matrix that I used here is actually is C inverse of the matrix that I need, right? So I need to correct it a little bit. So if I'm using this matrix, then I have inverse here if I'm using this matrix. All right, so inverse here. All this is just careful checks, but okay, following my notes, have this. Right. So actually I can go back from x bar to x double bar, right, and use the following, that x bar is cx double bar plus terms of degree greater or equal than 2 in x double bar, right? So I can actually continue this computation. So this equals to C inverse Q of x, and Q is bilinear. So that's what's important. In Q, I'll only have terms in x, terms which are simultaneously linear in x and y. Only these cross terms, remember? So therefore, I can just replace this with double bars with the price. Well, I'm using this, right? So therefore, with C inside, cy double bar, right? So I'm using this here. And these terms, they just can be factored. They will give us something that we don't care about. So these are terms of degree greater or equal than 3, right, in x double bar and y double bar. On the other hand, we can reiterate definition of Q, right? So we have x. Well, we actually have Q, but for different charts, right? So our Q actually depends on the chart. So actually, let me differentiate between Q related to this chart and Q related to this chart by adding indexes. So this is actually Q1, which is related to phi 1, right? Because we took this corresponding to just one line here, which is related to phi 1, right? And consider Taylor expansion in x bar and y bar. So this is really Q1 corresponding to this phi 1. But we can do this with, so this is Q1 here. But we can do this with Q2, just using definition definition right away. So we have this is the same as Q2 of x double bar, y double bar, plus terms, again, of degree greater or equal than 3 in x double bar, y double bar. And we compare So we computed this in two different ways. This one, and this is another result. So we actually have the following. We have that C inverse Q1 of any vectors actually, CV1, CV2. So here V1 and V2, so it's any V1, V2 in Kn is Q2 of V1 and V2. So now we need to take this and well apply it to so with some particular V1 and V2. So we actually take bracket. So let us fix. So fix some psi and eta. So these are vectors in G. Okay. Then we actually can compute the bracket, but we as we defined it. But the bracket for now depends on whether we compute it using phi1 or phi2. So let's again distinguish between these two by index. So this is bracket computed using phi2. And okay, let us just use definition. Okay, so I'm using this definition where phi is phi2, right? And q is q2, right? So I have by definition this equals to d e phi 2 inverse q, so 2 of d e phi 2 of psi d e phi 2 of eta. This equals to, and now we need to use, so in here let me take q, so I will take v1 to be d e phi 2 of psi and v2 d e phi 2 of eta, and then use this relation which is star. So this is star with such choice of v1 and v2. This gives me what? Well, this I don't change d e phi 2 inverse. Then I have c. So I transfer from here to here. So c inverse of q1 d e c times d e phi 2 of xi c d e phi 2 of eta. This. Okay, now I should remember what is c. C is written here. And so therefore, if I put, so c, so de phi 2 multiplied by c from the left, d phi 2 inverse cancels with this d phi 2, gives me d phi 1. On the other hand, let's compute this. So we have d e phi 2 inverse times c So this is d e phi 2 inverse, and sorry, c inverse here, right? So c inverse here gives me d e phi 2, and then d e phi 1 inverse, right? It goes d phi 1 goes to the right with inverse. So this cancels again, and we get d phi 1 inverse. So as a result, so this is d phi 1 inverse. And then q1, and then d e phi 1 of psi, d e phi 1 of eta. And this is by definition exactly what we call the bracket of psi and eta defined with the first chart. So actually we proved now that our bracket does not, it's just the same vector. This equals to this. And we have canonical structure on a Lie, on the tangent subspace at identity to and a tangent space to identity in our Lie group, which is called Lie bracket. So it doesn't depend on phi. Okay, we would like to work with this new structure. So let us actually compute Lie bracket for the following example. For GLN, whether K, whether R or C doesn't really matter. So my tangent space at identity, right, as a subspace is just all linear transformations of Kn. So these are all linear transformations of Kn. It doesn't really matter. So actually, these are all. You can think of it as all n by n matrices. Doesn't really matter if it's inversible or not. And this one is now much easier structure to think about than this one because it's a linear space. And on this linear space, we have a bracket, which is pretty abstract right now, but let us compute it in this case. So I have, so how to compute it? I need a group commutator, right? And I would like to, so I have some map. I need to choose some map around identity, right? So from some, this map will be actually from from U, which is subset in GLN, right, to K n squared, right? So this is a chart. This should be a chart of GLN, and the GLN is known as dimension of GLN is n squared. Right? What is this chart? I need to choose it, and I would like to send a matrix like this: 1 plus x, 2 x. The x is some matrix. Well, this is a chart which is centered, right? So x. So right. How I should treat x as an element in here. So x is a matrix with some elements, x1, 1, and so on, x1, n, x n1 x and n. And so these are n square coordinates that give me exactly an element in Kn squared, right? So for each matrix like this, its coordinates are these xij's, right? And we see that this is centered chart, meaning that if all coordinates are 0, then the corresponding element of the group is identity, as we wanted. So now we would like to take group commutator of two elements, and actually U coincides with GLN in this case. So almost coincide. Well, still we would like X. No, U is something dense in GLN, but still does. So let's see. No, I think it's okay. Yeah, U coincides with GLN in this case. Right, and so what is, we would like to take two elements and consider group commutator. So I take 1 plus x, 1 plus y, 1 plus x inverse, 1 plus y inverse. So here x is a matrix like this, y is matrix, right, with entries y1, 1, y1, n, yn1, yn, n. And we would like to decompose this, right? Look. So this is some matrix function, right? In variables x, ij, and yij, and we would like to consider Taylor series of this function of these variables, and we would like to consider well, quadratic terms in x and y. And so I will actually have so this Taylor series of this, if I start expanding this, will be 1, and then I have minus x, and then plus terms which are actually of higher degree. They are quadratic terms, but we will not need them because, because we need only bilinear terms, quadratic bilinear terms in x and y. And this one is expanded as follows: 1 minus y plus ... And if you start looking for, so if you start expanding this will be 1, and then plus xy minus yx, and then plus terms which are of degree, so terms of degree greater or equal than 3 in x, ij, and yij. And so we would like to take, so this is some expansion, and we would like to, so remember, so this is actually what? 1 plus x, 1 plus y, group commutator. This is our expansion of this. But then we would like to take phi, well, bar, right, which is coordinates of this. And we know how we compute coordinates in this coordinate chart. Just 1 plus this, we send plus x, we send to x. So coordinates of this will be, so I need to get rid of this 1. So it's xy minus yx plus terms of degree, again, greater or equal than 3 in x and y. And so, therefore, our Q of x and y, right? Well, should be like of x ij, right? Y ij. So this is exactly xy minus yx. So this is just commutator. And moreover, I can, I can identify my x with an element in GLN, which is tangent space at identity of G, which is this group, right? And well, my differential of phi then, right, is just tautological map. So this just sends x to x. So d phi in this case is just sends x to x. So we really computed that the bracket in this case of two elements is xy minus yx. So the Lie bracket in case of GLN is really just a commutator, and actually it will be true for any subgroup of GLN, and actually for any subgroup of GLN, its corresponding tangent space at identity will be inside all the n by n matrices, and the Lie bracket will be just commutator. We will prove it in a minute. Well, actually, maybe in the next lecture. So this computation is very important, and actually it is a general theorem that well, we will yes, so we will actually introduce general notion of Lie algebra, and Lie algebra is some vector space with additional structure, which is Lie bracket, which mimics properties of the Lie bracket that we introduced in tangent space. And general theorem says that it is always subalgebra, Lie subalgebra of this. It's called Edo theorem. And so this computation actually says that every Lie bracket is a commutator in a sense. So sometimes people just call Lie brackets commutators.